So what is a spanning subgraph? G is equal to V comma E and H is equal to V dash comma E dash. So H is a subgraph. If V dash is a subset of V and E dash is a subset of V. Right? So we know what is a subgraph and what is a spanning subgraph. Spanning is subgraph H is equal to V dash E dash with V dash is equal to V. That means H spans the whole vertex set of this. Spans the whole vertex set of G. So it's called a spanning subgraph. So it's a subgraph and it spans the whole vertex set. That is a subgraph. For example, one, two, three, four. What is this? There are 5 pages. This is my G and H is equal to. So this is my H. So H, if you see the vertex set of this H is same as vertex set of G. So this is a subgraph as well as it's a spanning subgraph. Is this clear?
Yes, sir.
Okay. So spanning tree means a subgraph. Let G be a connected graph. A spanning subgraph H is a spanning tree if H is a tree. H of G. So this, first of all, H must be a tree and H must be a spanning subgraph of G, then it's called spanning tree. So, for example, so you have got several spanning tree. This is one, T1, then this is T2, this is T3, this is T4, like this. So you have got several spanning trees. So now what happens? Suppose G is a weighted graph. So for example, some weights are also there. Suppose 5, 7, 8, 9, and 10. So if you see this one, it is 5, 7, and 8. And in this case, 7, 8, and 10. And this case, 9, 8, and 10. In this case, 5, 10, and 10. So these are the weights. So if you see the weight of the sum of all the edges, this weight of this is equal to summation of weight of E. E belongs to E of T. And for this particular graph, what is the weight? 20. For this particular graph, weight is
25.
25. This is 27. And this is 23. So out of these 4, so how many such spanning trees are possible for this particular graph?
Anybody can answer? What's the answer?
For given tree, how many possible spanning trees are there? Is there any formula?
There are two spanning.
Only 2. But already 4 are given.
Yeah, ma'am.
Just see for given graph.
It's minimum spanning tree.
For every graph there is 2.
No, ma'am.
For this graph only 2.
Okay.
And what is the minimum weight?
Okay.
20, same.
So weight of the spanning tree is sum of the weights of all the edges of that particular graph. Say, for example, these are 3 edges. So this 5 plus 7 plus 8, that is 20, right? So number of spanning tree for this particular graph, what will be the number of spanning tree? Can you tell?
Somebody is saying 2. I think Preeti is there, no?
Already I have constructed 4, right? Already T1, T2, T3 are 4, at least 4. So do you have more than this or you have less? You have one more. For example, you have more also. For example, something like this. This is another graph. So this is spanning tree. So what are the weights of this spanning tree? This is 7, 9, and 10. So this weight is what? 26. Right? So you have got many number of spanning trees. Now the problem is find a spanning tree of minimum weight.
So
Yes.
is there any formula for?
Sir, can we find out with 7, 5, and 9? One more. Is it possible? 7, 5, and 9.
7, 5, and 9 also is there. For example, this is
Yeah, this is
also there. 7,
Yes. 5,
9, 5,
and 5. Yes.
So this is 21, right?
Yes, sir.
This is 21. So,
Sir,
yes.
Sir, is there any formula for maximum number of spanning tree for any graph?
Okay. So, number of spanning trees. So, how many spanning trees are there? This is the question. Right. So G is there. Take any edge. E is equal to xy. Some edge. So count. So number of spanning trees of G containing X, not containing XY. Suppose, so I say that number of spanning tree of G, right? This is the formula for number of spanning tree of G. So number of spanning tree of G not containing XY, what will be the number of spanning tree? So this will be basically number of spanning trees of G minus E, right? Because E is not present. So even if you remove this edge E, so whatever the number of spanning tree of G minus E is there, it will be the same thing. So number of spanning tree containing XY, what will happen? So there is a contraction operation. Contraction operation means, for example, so this graph is there. Suppose 1, 2, 3, 4, 5. So 1, 2 is an edge, E is equal to this. So if you contract it, then what will happen? G contraction E is basically these two vertices you just merge into a single vertex. So this will be 5, 4, 3, and this vertex will become 1, 2. 1, 2. This is vertex called 1, 2. This is 1 dash. And the edges, for example, if you take this one and lift it and put over here, then there will be edge like this, and then there will be edge like this, right? Self loop, and this is the edge. So the self loop and parallel edges, you remove it, right? So after that, it will be the case. This is a new 1 dash vertex, right? So this is contrast.
So the parallel edges should include, otherwise the count will be reduced, right?
Yes.
But the edges importance. You can
So,
put the parallel edges. Yeah.
okay, so formally I'll define what is G minus E. So G minus E, vertex set of G minus E is equal to V of G minus XY union some X dash. So this XY is removed and then you put an X dash, and S set of G dash is equal to S set of, this is basically set of all XY such that, or UV, so that UV belongs to V, U not equal to X, V not equal to X, union, what happened, this X dash to A, such that XA belongs to E, or Y A belongs to. So for example, if I want to contract it, 1, 2, 3, 4, what will happen? 1 and 2, what is that will be? This is 1 and 2, this is 4, 3 and 4, this will be 1 as well as 2, right? So these two edges will go, and this vertex is new vertex is addition to 2 is addition to 3, so this new vertex will be addition to 3, and this 1 is then 1 is addition to 4, so the new vertex will be addition to 4 also. So after that you remove it. So this thing, if you remove it, so you will have something like this. So we are talking about simple graph. So this is basically edge contraction, and removal is basically just remove it, right? This is the removal, and the other one is edge contraction, right?
Yes, sir.
Yes or no? Okay. So this is basically, so there is a formula. Number of spanning tree of G is equal to number of spanning tree of G minus XY plus number of spanning tree of G XY. That means you contract this thing. So you can use the this recurrence relation to count the number of spanning tree of this. So let us take a simple example how to find out. So
Sir, what is the last term?
so after this is after contracting the edge XY, whatever the graph you get, so number of spanning tree of that you add it, because these are the spanning trees of G which will contain XY, and these are the spanning tree of G which will not contain XY.
G minus XY plus.
This is G minus XY plus spanning tree, number of spanning tree of G contraction XY. This is contraction XY.
Okay, okay.
Contraction XY.
Okay,
Right.
okay.
So let us take this one, this particular example, right? Number of spanning tree of this, right? So if you take, this will get number of spanning trees. Suppose this is my X and this is Y. If I contract this one, including XY, how many spanning trees, not including spanning trees are there? So these are the number of spanning tree of this. And if you contract it, what graph you'll get? These two vertices will be 1, and this will be 1, this will be 1. So this, after removing this one, these two will be going through this, and 2 parallel edges will be. In fact, it will be like this, and it will be like this. If you remove this self loop, and parallel edges, it will be something like this and this, right? So
parallel edges we may not remove, sir, because parallel edges will contribute to the number of spanning trees. Parallel edges will contribute to the number of spanning trees. We cannot remove, I think so. Root maybe we can remove, because that will not give any.
So that
for example, yeah, for example, here for this case, we have some See, after making this one, you have a path of length 2, right? You have only one spanning tree.
Yeah.
Before making it is more than 2.
Okay,
more than
okay.
one.
Okay. So this parallel thing will be there also. Okay, yeah, great. Yes, right. So only self loop you remove it, right? So now what is the number of spanning tree of this? What is the number of spanning tree? This is a cycle. If you remove any edge, that will be a cycle. So it will have four spanning trees, right? For example, if you remove, this is 1. If you remove it, the 3 edges will constitute a spanning tree. So if you remove any of the edges of the cycle, it will have a spanning tree. So you have got 4 spanning trees, right?
Yes,
and
sir.
for this particular graph, how many spanning trees are there? So I will take this edge and this edge. So there are 2 choices. 2 into 2, 4. So 4 plus 4 is equal to 8. So containing this 4 will be what? So this edge is there. So for example, original graph, if you see, containing this edge xy you take, and now I can take this one. This is 1, this one, and this one. This is second, this one, and this one. Third, and another is this, this, and this. So this is the 4 spanning trees of this particular graph containing the edge xy, and not containing this xy, you have got 4. So 4 plus 4, 8. So this graph has 8 spanning trees. Is this clear?
Yes, sir. Yes.
Yes.
Yes, sir.
Okay. So this is one thing. So already we have seen the Laplacian matrix, right? So A is adjacency matrix.
So sir, for any n, it is n to the power n minus 2.
So that will be for complete graph. That I'll come here. This is for any arbitrary graph, right? So this recurrence formula for arbitrary graph, any graph. But the n raised to power n minus 2 is the for complete graph, right? So how many spanning trees or level spanning trees are there? That means how many spanning trees of Kn are there? So that will be n raised to power n minus 1. I will tell why it is. Adjacency matrix we know. This is A is the adjacency matrix and D is the degree matrix. DII is equal to degree of BI, and then other elements are there. Other elements are zeros. So the Laplacian of G is equal to D minus A, or A minus D, you can take one of the things. So diagonal matrix minus the adjacency matrix you take. So that is Laplacian of G. And now you take if you remove any rows and corresponding column, that is called minor, right?
Yeah. Yes.
So minor. For example, if you remove of any row, so maybe first row and first column, and take the determinant. So that is basically number of spanning trees, right? For example, for K4, what will be the Laplacian of G? Laplacian of G is equal to, what is the degree of each vertex is 3. Then vertex is vertex 1 is minus 1, minus 1, minus 1, minus 1, 3, minus 1, minus 1, minus 1, minus 1, 3, minus 1, minus 1, minus 1, minus 1, 3. So this is basically L of K4. So you just remove this row and this column. What is the determinant of this? Determinant of 3 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 3. What is the determinant of this? Somebody can calculate and tell me. it is, let us calculate this thing, right? So this is what? 3 into 9 minus 1.
Minus
3
1.
into 8. 8
Plus
plus
1
1 into
minus 3 minus
minus
1.
minus 3 minus 1 minus 4
Oh,
minus
again minus 1.
into
1 plus 3. It means 4.
1 plus 3
Just put there right. 4.
minus 1 minus 3 minus 1
The
3 4
total-
right?
Yeah,
4.
the 16 will be answer, sir.
16 is the
16.
So are they equal to 16 or what? No,
Yes.
16
16.
minus 16, right? So is it 16? It should be 8, right? Should be 8. K4 2 raised to power n minus 2. And no, n raised to power 4 raised to power 4 minus 2 is equal to 16. Right? For complete graph, there are 16 spanning trees, and this is basically that you will got. Just a minute, I'll open my door and come. Okay, so you got a formula how to find the. So this theorem is called the matrix tree theorem. Matrix tree theorem. Right? Number of spanning trees of this is basically the minor of the n minus 1 by n minus 1 minor of the Laplacian of this particular graph, complete graph.
Any minor, sir. Any minor.
Any minor.
Yes. Any minor.
Any minor of n minus 1 by n minus 1. And this is true for any graph, including complete graph. Right? For complete graph, what will happen? Suppose Kn is there. Right? Kn is there. So it has got n raised to power n minus 2 spanning trees. Right? But this formula is for general graph. Matrix theory is very powerful technique. It gives you now find the Laplacian of this matrix and take the minor. That determinant n minus 1 by n minus 1 determinant the number of spanning trees of such a graph. And
Sir,
then
excuse me. Sorry. Yeah, you are saying that any minor of this Laplacian is
same. Sir. That will be same.
Determinant of any minor of the Laplacian is same.
Same.
No, I think, sir, we have to consider for order n minus 1
Oh, n minus 1.
or
N minus
Yeah.
1 by n minus 1. If
N
you
by
remove
n, yeah,
any
that's
cell,
okay.
here
corresponding
we are
column.
considering.
Right?
But it
So
is true for any minor of order.
of
Yeah.
order n minus 1. Right? And this is another, this is a general also formula. It is also a reference relation to find the number of spanning tree for any general graph. And now this is for complete graph. This is the formula. Right? So number of spanning tree is exponential of a graph. Number of spanning tree, note, number of spanning trees can be exponential for a graph. First of all, it should be a connected graph, right? So now, the MST problem is that MST find a spanning tree T of G of minimum weight. weight. And weight function is weight from E to R plus is there, right? Positive weights are there. WE is greater than equal to 0. So given a connected weighted graph, given a connected weighted graph. Weighted graph means there is a weight function W, which is from E to R plus. That means weight of each edge is greater than equal to 0. So, and connected graph is there. So it has at least one spanning tree. And number of spanning tree can be exponential in number. So you need to find a spanning tree T of minimum weight. So this is basically minimize weight W of T. T is a spanning tree. So this is the problem we are built with minimum spanning tree. Right. So before going to the slides, let's see. So minimum spanning tree need not be unique. MST is not unique. For example, 1, 1, 2, 2. How many MSTs are there? How many spanning trees of this graph are there?
4.
4. How many MSTs are there? Out of these 4 spanning trees, how many are having minimum weight? 2. So what are those? Because this is 1, 1, 1, 2. Sorry. One, 1, 2. So this is 4 is the weight, minimum weight, and that you need to find out. So we know that this MST is connected and acyclic also. Connected, acyclic, M is equal to N minus 1. So all these things are true. So we need to have N minus 1 edges. So there are 2 popular algorithms. One is Prim's algorithm. Another is Kruska's algorithm. So these 2 are important algorithms. There are many other also. So we are going to see an algorithm called Prim's algorithm, and then I'll go to the slides. So what the idea is that, so for example, let me take one example first and then. So the vertices are 1, 2, 3, 4, 5, 6, 7, and 8. The weights are say 2, 3, 4, 2, 1, 2, 3, 2, 5, 2, 2, and 1. So the idea is that you start with any vertex. Start with any vertex, maybe say 1. So from 1, you try to grow a tree, and then when it contains all the vertices, so it will become a spanning tree. So what will be the, suppose out of 1, you want, how many edges are going out of 1? How many edges are incident on 1?
2.
2 edges. So, and since we are trying to minimize the total cost of the spanning tree, which edge you would like to have out of these 2 edges?
2 with weight 2. 1 to
2. So 1 to 2 you take it, right? So I'll just maintain the set S. S is equal to 1. So I'll find out S to V minus S all edges going from S to B minus S and select the minimum cost edge. So, so in this case, only two edges were going. So these two edges are going. I selected the minimum cost edge, that is 2, and then we added. Now, after adding, now I add 2 to S. So S is equal to 1 and 2. 2 is added to S. So S to B minus S, how many edges are going? So S to B minus S. So my S is like this. S is this 2. This is my S. S to B minus S is basically these edges are going. Right? So out of these edges, how many edges are there? 1, 2, 3, 4. So which is the minimum cost edge going from S to B minus S?
There are more.
More, but minimum cost is 2. There are more, so you can select any one. So tell me which one you want to select. 2, 8, 2, 7, 2, 3. These are the 3 edges of cost 2, and then 1 to 4, that is of cost 4. So you select me one of the edges. Which one? You tell me. 2 to 8, say.
3.
Huh? 2 to 3, okay. 2 to 3. So edge cost is 2. This is also 2. Just 1 minute. I have to open the door. Okay, so sorry. Okay, so we have added second edge. So now what will be my S? What will be my S?
1, 2, 3.
1, 2, 3. 1, 2, and 3. So S to B minus S. So how many edges are going? Several edges. So what is the minimum cost edge which is going from S to B minus S? So there are 3 edges. One, it is going 4. That is 4. Edge cost is 4. From 3 to 3 to only this cost is 2. From 2 it is 2, 2. So again the cost is 2. So select, give me a cost of edge of cost 2. Select one. Yes. So I can select, so 2 to 8.
5. Okay.
2 to no, 5 is not there. 5 is this. No? 5 it is not there. From S to B minus S. The
No, in our case, S equal to 1, 2, 3. 5 may be the option, right? 3, 5 may be the option.
3, 5 may be option. Okay, I'll select the 3, 5.
No, your choice, sir. Sorry. Simply I said you asked.
Okay, 3, 5 doesn't matter. 3, 5. What is the cost of the edge is 2. Right. Okay. So then you add S is equal to 1, 2, 3, 5. From S to B minus S, what is the minimum cost edge which is going? That is 1. This is 1. Right, because other edges are the case. So this is 1. So next from, so S will be, you add 4 over here. S is equal to 1, 2, 3, 4, and 5. So S to B minus S. Now if you see several edges are there, so I can select 8, 2 to 8. So the cost is 2. And after that, you select 8 to 7 will be there, the minimum cost edge. 7, this is 1. And then after that, only edges which are going from S to B minus S, only 6 is in B minus S. So 3 and 5. Out of these 2, 1 will be 3. So that is 3 to 6 is 3. Is this clear? Right?
From 7 to 6 also you can do that.
7 to 6, the cost is 5.
Cost is 5. Yeah.
And 3 to 6, it is 3.
Mm.
Acha, tell me now, anytime we selecting the edges, one vertex is in S and the other vertex is in V minus S. So the vertex which is in V minus S, what will be the degree at that point? When you add that edge to the existing tree, existing graph, what will be the degree of that new vertex? So if you see, for example, first edge we added 1 to 2. So the degree of this vertex was 1. Next vertex we added is 2 to 3, this edge. So 3 degree was 1. Then 3 to 5 we added, 5 degree was 1. And 5 to 4, that we have added, degree of 4 is 1. So like this. So the moment, since we are adding an edge from S to V minus S, so always the graph is acyclic. So we are maintaining acyclicity. Acyclicity is maintained. Plus, how many edges we are adding? Because S singleton set 1 was there, so we have added, after adding one edge, the cardinality of S is 2. So starting from cardinality 1, it is going to cardinality n. So how many edges we will be adding? N minus 1. So acyclic and n minus 1, we have already seen the characterization. A graph which is acyclic and having n minus 1 must be connected also, and which is a tree. So this will become a tree. So
how we are saying always after getting this algorithm, so you will get a acyclic graph. How one can prove, sir?
okay, how I? So for example,
Because see the random maybe you are giving some way.
oh,
So
no, listen.
Yeah,
So here S, this is the what it says. So this is my S now, right? Suppose 3 edges have been added, and this is my V minus S, right? So after that, I always constructed add an edge going from S to V minus S, something like this, anything like this. So this degree of this vertex at that point of time is 1. So it is not creating any cycle at that point of time. Right? Yes. I'm not adding two vertices of S. No, I'm adding an edge whose one endpoint is in S and another endpoint in V minus S.
Okay, so the particular vertex that may be adjacent to some vertex in S
Only
also.
one vertex of S, right? So this kind of edges will go. And the moment I have added, so this vertex I put in S, so S will be like this, S to V minus S, I always consider. So the graph,
Okay.
the set of edges in S now will induce a connected graph, and V minus S is the other vertices. So from S to V minus S, several edges are going. One of the minimum cost edge from S to V minus S, I'll just add it. Right?
Okay.
But so that will be a tree. But what is the guarantee that it will be a minimum spanning tree?
Yes.
Why the weight will be minimum?
Excuse
Each
me,
and
sir.
every step you will place. Yeah.
Yes.
So why have you written this n minus 1?
Why it will be?
So,
Oh,
so why it is n minus 1?
edges. No, number of vertices will be n, because S I am starting with 1, and when S is equal to V, I stop. So each time I keep on adding one vertices. And okay, how many edges I am adding? How many times I am iterating? Yes.
There's a disturbance.
I think mute. I think somebody is talking. So I think.
Yes, sir.
I thought of they are speaking Hindi.
Okay, no, somebody is there. Okay, so how many edges I'm adding?
n minus n.
n minus 1 edges.
One
So
edge.
total number of edges is n minus 1. So, and always I maintain the acyclic. So far selected edges will form an acyclic graph. So at the end, I have the graph will have n minus 1 edges, and this graph is acyclic graph. So it must contain it must be a tree. Right? So the algorithm is like this. So S is equal to 1, say any vertex you take, while S not equal to V, do select a minimum cost edge from S to V minus S, minimum cost edge xy from S to V minus S, such that x belongs to S and y belongs to V minus S. And then say E dash is equal to phi, E dash is equal to E dash union xy, S is equal to S union y, and continue. So each time if you see in the while loop, I'm adding an edge going from S to V minus S. So V minus S is an independent set. So far, that means no edge is incident on V minus S. All the edges whose endpoints are there that I have collected and put in set S. So always it is going from S to V minus S. So this in this step maintains the acyclicity. So each time the set of edges is not forming a cycle, at the end also it will not form a cycle. And since each time I'm adding one vertex to S, initially a singleton vertex is there, this while loop is running for how many times? N minus 1 times. N minus 1 times. N minus 1 times, so N minus 1 edges are added. So acyclic plus N minus 1 edges, that will become a spanning tree. Is this clear?
Yes, sir.
Yes. But it is just an algorithm. It may not, we have to prove the correctness. Correctness means why it should, or it produces a minimum spanning tree. And MST. There are several MST we have already seen. So we have to, this is called proof of correctness. This thing is answer to this is called, you have to write a theorem that is called proof of correctness. So we'll see in a moment. And now, so how much time it will take? So for example, S is like this. 1, 2, 3, 4, 5, and 6 vertices. So from this vertex, several edges are going. From these vertices, several edges are there. These several edges are there. These several edges are there. So out of these edges, I have to select a minimum cost edge. So how do you find? How much time it will take to find the minimum? So for this vertex, I'll take. For this vertex, I'll find out of these two, which is a minimum. I take this is minimum 1. From this, I find out all the edges going from this vertex, find the minimum. This minimum is greater than this minimum. I will say that this is the next minimum. So after that, for this vertices, all the edges going. So I have to find out the what? Adjacency list of this particular vertex. All the edges I found out and find the minimum cost. And this minimum cost is greater than this minimum cost, then this will be a minimum. It is smaller, then this will be a new minimum. So like this, if I have to scan through the adjacency list of all the vertices of S, so that may be order of n plus m time, right? So how many times each time I have to do it? So maybe n times you have multiply. So the algorithm will be polynomial. At minimum thing that it will take at the most nm time, but it can be done in lesser time also if you use a proper data structure. But so this one is a polynomial time algorithm. And polynomial time algorithm, the first thing, given a problem, is it possible to design a polynomial time algorithm? Is it fine at this point? Yes.
The order of, sir, 1 minute. So you are writing order of n plus m, right?
Order of n plus m is the least size, list of adjacency list of all the vertices. This will be what? How many vertices will be there? Degree of this vertex, degree of this vertices, degree of this vertices. So sum of the degrees order of n plus m. So these many elements, I have to find out the minimum. Suppose 10 elements are there. How to find the minimum? 10 step you have to see. Minimum is equal to first element. If minimum is less than second element, then that will be the minimum. Minimum is greater than the second element. Second element is the minimum. So this is basically I can find the minimum in order of n time. N elements are there. So, but this size of this list is order of n plus m. So you have to find. We can find the minimum in order of n plus m time. But now, how many times I am iterating? N minus 1 times. So you multiply n minus 1 over here. So it will get order of n square plus nm. M is always greater than equal to n minus 1. So it will be order of nm time. Is this clear?
Yes, sir. Yes, sir. Yeah.
Okay. Okay. So, but the proof of correctness is still pending. That we'll see a generic proof. Okay. This is basically Prim's algorithm. The algorithm is clear to you or not? Let me take one more example, and you should now tell me which edges I should pick. So these are the distinct costs are there. 1, 2, 3 up to 10. 10 edges are there, 10 costs are there. Suppose I start over here. So which edge I'll select? Edge of cost?
1.
So this will be selected. So after that, which edge will be selected? Edge of
2.
cost? 2.
Mm.
After that, 3 will be selected. After that, 4 will be selected.
4.
Then when you go to 5, 5 will be all the vertices in both the endpoints are in S. So 5 will not be the S to B minus S. Then you have to go for what?
6.
Not 6. 6. 6 will
Yeah.
7 and
8
7, and then it will be 9.
9.
Right. So you can see that you have only one choice all the time, right? Yes or no?
Sir,
Yeah.
we may go for after 4th, we can go for 8 instead of 7.
Why 8? Because
Least one we need. Yeah.
least one is which one will go?
Okay, fine.
Least one is 7, right? These are
Right,
edge
sir,
cost.
Right. Right.
These
Okay.
are
This
edge
is
cost.
possible. Right, sir.
1, 2. This one is 3, right? Okay. So in this graph there is a unique minimum spanning tree. That is another thing. This graph has exactly 1 MST.
Because
That's
all
why
levels are distinct.
all edge costs are distinct.
Yeah.
Right. So this is one thing. If weight of E not equal to weight of F for any two distinct edges E and F, then G has a unique MST. Right. So this graph, all the edge costs are distinct, so it has a unique MST. So how do you find? From S to B minus S, when you see, you have to find a minimum cost edge going from S to B minus S. S to B minus S, you have to find a minimum cost edge. This, if you always find a unique minimum, then this will be the case. So in this case, since distinct are there, all the edge costs are distinct. So out of all those things, at least exactly 1 will be the minimum, right? If this property is there. But even if this property is not there, all edges are not distinct, still you may have a unique MST. For example, when you'll have, okay. So for example, in this case, 1, 2, 3, 4 is 5. Then 6, 7, 8, 9 up to distinct, and this 5 is there. 9, 10, 11, 12, and 13. So now you can see this edge, and this edge, both the cost is 5 only, right? But still this graph will have a unique MST. Why? Why is the case? These edges are special edges. These are cot edges. This will be present in every MST. This will be present in every MST. These two edges. These are cot edges.
Every
And-
spanning trees also.
Every spanning tree also, not only minimum spanning tree. Every spanning tree will contain these two edges. And in the cycle, all the an edge which is part of the cycle, no two edges in a cycle are having same edge cost, then you have a unique MST. Right?
Yes, sir.
Okay. So at this moment, at least you know the algorithm. So now another algorithm we'll do, that is called Kruskal's algorithm. Right. The Kruskal's algorithm is like this. So for example, what you do is the sort the edges in the decreasing order of their cost. Let U1, E2, EM be this ordering. So you maintain a count and I is equal to 1. And while count is less than n, minus 1, you do. And E dash is equal to 5. Right? So what do? You keep on repeating that. So I is equal to 1 if G dash is equal to V, comma V, comma E dash union EI is acyclic E dash is equal to E dash union EI. That means you are checking one edge, and so far selected edges, it is not forming any cycle. Then you add that edge and you have successfully count is equal to count plus 1. That means increment the count and increment the count, and I is equal to I plus 1. Okay. I is equal to I plus 1, and then continue. So that means you have to, after sorting the edges in the increasing order of their cost, keep on checking, and so far selected edges is not forming any cycle, then add it, otherwise ignore that edge and go to the next edge. Is the algorithm clear or no? I'll illustrate it, but see. First we have to do, you have to arrange the edges in the increasing order of their cost, non-decreasing order of their cost. This thing is fine?
Yes, sir.
Yeah.
Yes, sir.
Second one is, you start from U1. U1 so far you have not selected any edge, so U1 is not going to form any cycle. So U1 will be selected. Then suppose you have selected up to, consider up to E1, E2, EI, and you have selected certain edges. Then now you are considering EI plus 1. EI plus 1 is not forming any cycle with so far selected edges. You add it, otherwise ignore it and then go to the next edge. And you stop as soon as this count becomes n minus 1, you stop. So you have selected n minus 1 edges and you are maintaining also acyclicity. And now basically you'll get a spanning tree. So let us take one example first and then you will understand it. So take this particular graph. Take a slightly bigger one. So this is the edges are say A, B, C, D, E, F, G, H, I, J, K, L, M. And the cost of the edges is say, this is 2, 1, 2, 3, 1, 1, 1, 2, 2, 3, 3, 5, 5, like this. So if you now tell me what are the edges in the increasing order? E, F, C, then H. This is all ones, 1, 2, 3, 4 ones. Then you have to see the 2, A, B. This is 2, then A, B, and then G, H. G, H, all 2s. Then 3s. 3s are D.
The two edges were present.
Huh?
Two edges were present.
2 edges are present means what? Acha, E, F, C, H. देखिए E, F, C, and H. Right, this is 1.
Yeah, A, B, G,
A, B.
H, again one more H.
Okay, H is not. This is H or what? No. A, B, C, D, F, G, H, I, J, K, L, M. This is M, right? This is M. This is M, right? Right. Then D. 3 is D. 3, and then I and J. I, J. And then you have got E and K. E and K. So this is the list.
One
Right.
edge, I think you are not counting.
Huh?
One edge you are not counting.
Which edge?
The last one, maybe 3, 3 you are writing from the right side.
Huh?
Bottom. K edge is there no before.
K. This is my K, right? This is K.
No. See the K before K incident to some triangle, right? On the
Acha,
triangle, three
E,
triangle.
acha. K, E, and M. A, B, C, D, E, F, G, H, I, J, K. This is L, right?
No, you are not
L.
giving the label at all. That's what. One edge you are not giving the label. That's what.
Which one?
M, then they are neighbor from the right side.
Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Acha, this one is there, right? This is I'll put it as 10, right? And this is after M, this is N. So this is N. Okay. So now I keep on adding the edges which are a minimum cost and not forming the cycle. So I'll put the red mark. So E edge, edge E. So I have added this one, right? Then F, E and F is not forming any cycle, so I'll add it. So I have added it. Then it is C. C also is not forming any cycle, so I'll add it. C also I added. Then M. M also is not forming a cycle, I'll keep on adding it. M also it has it. Then A will form a cycle? No. A also I can add. B, when you add B, it is forming a cycle or no?
Cycle.
Cycle. So this will be not considered. And then after, after then G, if I add, it will forming a cycle. So I'll ignore it. Then H
Age we can consider.
H I can consider.
Mm.
H is added. Then D if I put it, it will form a cycle. So it will not be considered. Then I also will form a cycle. So it will not consider. Then J
J can consider.
J I can consider, right? So J is added, right? Then L, this is L I can consider, right? L I can consider. Then K,
No.
K, if I do it, that will form a cycle. So it is not. I need not to. I think I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices are there, 8. Why then the count will become n-1? After that, whatever edges are there, I need have to consider in fact. So this will not be considered. Even I will not even test it whether to be included or not. So now since I am always checking the so far selected edges is forming a cycle or not. So I am always maintaining the acyclicity. And I'm count is equal to n-1, I'll stop only when it is n-1. And we will be able to add n-1 edges because this is a connected graph, and connected graph by definition will have a spanning tree. Why it will be a spanning tree? Every connected graph has a spanning tree. Why is this case?
Successfully remove an edge, we will make.
Okay, successively edge, removing edge from where? So for example, from the graph. For example, this. The moment I remove this edge, after that the graph becomes disconnected, right?
No. Successfully remove once you have to give the guarantee that the graph is connected.
Connected. So which edges will definitely will make my life easy? So always I have to look for a cycle. If the graph has a cycle, if graph has no cycle, I'm done because connectedness is given and acyclicness is given. So I'll look for a cycle and delete the edge. So I delete this particular edge, right? So again, from this graph, I look for a cycle and delete one edge, right? So delete one edge, right? So after that, the graph has no cycle, I stop. So I just keep on breaking the cycle one by one by removing the edges. And at some point of time, since if you remove an edge from the cycle, you can prove that it doesn't make the graph disconnected. So the caught edges are only edges which are not part of any cycle. So caught edge I'm not going to touch, only remove the edges from the cycle one by one. So as long as there is a cycle, so at some point of time the graph is acyclic and still connectedness is there. So the graph becomes a tree, which will be a spanning tree. So every connected graph is a spanning tree. So we'll be able to add n-1 edges because we are given a connected graph, connected weighted graph, and we are always checking the edges are not forming any cycle. So we are guaranteeing that it is acyclic, and hence, and at the end we are able to add n-1 edges, so it becomes a spanning tree. So this particular thing, how many times we are iterating? n-1 times, right? So n-1 times into what we are checking? We are checking the acyclicity. So how do you check whether graph has a cycle or not? we can use BFS or DFS, BFS or DFS, and which is going to take order of n plus m time. So it will be order of n plus m, which is going to order of n m time. Is this clear? Yes or no?
Yes, sir. Yes.
Yes. So here also we are successfully able to now construct a spanning tree, and we think that it is of minimum cost, but there is no guarantee. Finally, you have to prove that the weight of this spanning tree is as minimum as possible. That we need to prove. So proof of correctness for both the algorithm is still pending. So this is basically, at least algorithm, you know, what is Prim's algorithm and Kruskal's algorithm, and logic is you have understood or not?
Yes, sir.
Yes. So to prove this one, so there are a proof by method of contradiction, right? Prim's algorithm and Kruskal's algorithm, but there is another way to do that thing. So we'll see. Not only this, these are special cases of a generic method. So we'll see that particular method, and we'll see that Prim's algorithm and Kruskal's, and that method will guarantee a optimal or minimum cost spanning tree, and Prim's algorithm and Kruskal's algorithm will be special cases of that particular algorithm, right? So let me switch to my slides. Okay, so this is a visible minimum spanning tree, and we have seen this particular characterizations in the last class. Fine? Yes or no?
Yes, sir.
So we will be, the Prim's algorithm, the Kruskal's algorithm uses this characterization, because each time we are checking the acyclicity and we are adding n-1 edges, and Prim's algorithm, this is Kruskal's, and G is connected and m-1 edges, this is Prim's. Because the so far selected edges in S forms a connected part. So this is connected, keep on growing the tree. And when you include all the vertices, the number of edges will be n-1 and it's connected, right? So this is basically idea of Prim's algorithm. But we'll show something. Okay. So minimum spanning tree, a tree connected as a graph which contains all the vertices of graph. Minimum spanning tree, in this case, these edges, if you take, they form a minimum spanning tree. And the graph is not connected, then every component will have a tree. So you will get a spanning forest. So each component, you can find out the minimum cost tree in each component and combine that thing, that becomes a spanning forest. Okay. The weights are basically, for example, see the situation. So these are the vertices, and between these two vertices, there is a road which is going to connect it. So these are the weight of this particular road, or cost of maybe repairing the road. And suppose you are required to maintain the road in such a way that at least any person from the house will be able to go to any other house using the new roads or constructed road, and the cost will be as minimum as possible. So because connectivity means there is a path between any two houses, so it must be a connected graph. And since is the positive cost of repairing, so there will not be any cycle because we want to minimize it. So it becomes a minimum spanning tree. So spanning tree, by the way, has other applications. Maybe tomorrow time permits, then I'll give an overview of the applications of graph, and then we'll see the tutorial sheets, right? So you have a T of V, comma E is connected, this, and then we want to minimize basically the sum of the cost. So that is minimum thing. So find the least expensive way to connect a set of cities, terminals, computers, etc. So these are basically some kind of if you want to have a network, so basically this is one way you can connect, so that this is the connecting wire, so information will flow from one of the node to other computers, right? So the MST has other applications. I will show you. Okay. So this is another this is a problem I was looking for, or I was telling that a town has a set of houses and a set of roads. A road connects two and only two houses, any road segment. A road connecting houses U and V has a repair cost weight of U, V, that is a positive cost, and repair enough and no more roads such that everyone stays connected and total repair cost is minimum. So the solution will be a minimum spanning tree. Okay. Say, for example, this particular graph. So how many spanning trees this graph has? Yes, please. Minimum spanning tree is not unique. For example, this particular graph has two MST. For example, this highlighted edges, this and this is one thing. Of top one and this one you take, this is another. So the graph has two distinct minimum spanning trees. So number of minimum spanning tree can be large, also exponential. So it is a challenge to construct a minimum spanning tree of spanning tree of minimum cost. Already you have seen the number of spanning trees. Number of spanning trees can be exponential. Out of exponential feasible solution, you have to select a feasible solution of minimum cost. So that is a challenging problem, but unfortunately, this problem admits polynomial time algorithm. One such algorithm we have seen as Kruskal, the other one is Prim's algorithm.
So, sir, Prim's or Kruskal, both algorithms can be applicable for the dense networks also.
Okay, so the complexity we have used a crude estimate. But we have not used the data structure. I have not used the data structure. So basically the Prim's algorithm, the sorting M nodes will be sorting of the Kruskal's algorithm will be order of M log N, because M edges to be sorted. So it will be M log N, M log M will be there. So order of M log M, and which is equal to order of M log N, because M can be order of N square. So it will be 2 will come out. So it will be order of M log N. And Prim's algorithm will be order of M square. If you use a heap, you can now slightly decrease it. But if you use only array, it will be order of N square. Heap, some further implementations are there, a better data structure. But even if you take this simple thing, so which one will be better for the density?
It is Kruskal in that means Prim's is
Prim's will be better for dense.
Yeah.
Dense means M is equal to order of N square. So the number of edges is large. That means about order of N square. Then it will be N square log N. So Kruskal will be worse than the Prim, right? But sparse graph means M is equal to order of N. If that is the case, it will be N log N. If this will be order of N square. So Kruskal will be better for sparse graph, and Prim's algorithm will be better for dense graph. All right. Okay. But there are some important data structure called heap. So the heap implementation of Prim's algorithm, you can get a better complexity. Okay. So let us see some properties of this before designing the algorithm, which edges should be definitely be part of some MST. So let E be a minimum cost edge of a connected weighted graph. Then there is an MST that contains E. So the minimum cost may not be unique. You may have so 1, 1, 1, 1, several such one cost edge will be there. But whatever edge of cost 1 you take, there will be always a minimum spanning tree containing that. So if you start building you're developing your algorithm and select any minimum cost edge, and if you keep on growing it, you are not going wrong, because this theorem will guarantee that at the end there will be a minimum spanning tree containing that particular thing. So at that point you are not going wrong. Is that clear? Why this theorem will be important in designing the algorithm? Let us prove it that why definitely there will be a minimum spanning tree containing this edge E. Have any question? Okay. So let T dash be an MST of G and let E be a minimum cost edge. So there may be more than one, but I have selected only one, that is E. If T dash contains E, then we are done. If T dash doesn't contain E, then what will happen? You add E to T dash. For example, T dash will be something like this, right? And E will be like this. This is my E. If I add it, what will happen? In the there will be a unique cycle. Unique cycle. Now in this cycle, there are at least two other edges are there, because cycle length will be at least 3. So there may be more than 2 other edges. This cost was minimum in the whole network, whole graph. So what will be the cost of this E? So you select any edge. So this is my E and this is my F. So what can you say about cost of E and F? Weight of E must be less than equal to weight of F. F is which edge? F is another edge from the cycle. That unique cycle which is formed after adding E. From the cycle, this particular cycle, you have now selected one edge F.
I think state inequality, sir.
Yes.
I think state inequality. Weight of E less than weight of F, right?
Weight of E less than equal to weight of F.
No, not equal. State inequality. Otherwise, F will be.
Oh, no. I'm saying the minimum need not be unique minimum. Na? So this can be. So less than equal to this.
Okay.
Right?
You are saying that all minimum weight cost would be there in
MSD. All, not all. Take any minimum cost, there will be a spanning tree. For example, all these things are 3, 3, 3. All these things will not be together in one MST. They may be in separate MST.
Okay.
Okay. So after adding E, we have a unique cycle. Whatever the edge you take F, weight of E will be less than equal to weight of F. And from the cycle, if you remove this edge, you remove this edge. So once you remove it, right? So again, you will form a tree. Again, you will have a tree. That tree, what is that tree is basically T. T is equal to T star minus F. So you have removed the edge F, and now you can see that weight of E is less than equal to weight of F. So weight of T is less than equal to weight of T dash. So, and T dash was a minimum spanning tree. So so this E and F will have same cost. So weight of T, T also will be an MST. And now T is going to contain the edge E. So this is my T. After removing this edge F, I got the tree T, and T is going to contain the edge E. So every minimum cost edge must be present in some MST. Is this clear?
Yes, sir.
Yes, sir.
And what is the implication of the theorem for algorithm design? So given a graph, for example, something like this is there, 1, 1, 1, 2, and 3, 3 is there. I can select anyone freely. This theorem is going to guarantee me, so I'll select this edge, right? So I select this edge. If I select first edge, I'm not going to go wrong, because this theorem is going to guarantee me that there is a minimum spanning tree where this edge is present. Yes or no?
Yes, sir. Yeah.
Yes. So this is the importance of this particular theorem. So theoretically, it may not be very important, but it is basically important for designing algorithms. So yeah, Kavaskor was asking what kind of theory you develop. So this kind of thing, small thing you have to develop, and then together you use it to show the correctness. Okay. What about heaviest edge? Heaviest is maximum cost edge. let E be a maximum cost edge of a cycle C of a connected weighted graph. So if you take a maximum cost edge, which is not part of the cycle, that will be a cottage, that will be part of every MST or every spanning tree. But if you take a maximum cost edge of a cycle of a weighted connected graph, then there is an MST that doesn't contain E. So that means if you delete a heaviest cost edge from the cycle and then remaining graph, again you look for a cycle and look for a heaviest cost edge in that cycle, keep on repeating this process, then at the end there will not be any cycle. Whatever you left with, that will be again a minimum spanning tree. Is this clear? The
Yes,
idea?
yeah.
Okay.
Yes,
Yeah,
sir.
idea is okay. Yeah.
But now suppose n is equal to 1000 and around, if the graph is dense graph, so 1000 square edges are there. So you have to keep on removing. Most of the edges are there in the cycle. Heaviest edge one by one, if you remove it, it will take many steps to remove all the edges. Then adding 999 edges, right? So 10,000 square minus 999 edges, you have to keep on removing one by one, finding a cycle and looking for heaviest cost edge. So though theoretically it gives you a method for constructing minimum spanning tree, but the method may not be very efficient, right? So let us prove why it should be the case. The idea is exactly same. Let T be an MST of G. If T doesn't contain E, we are done. If not, you remove the edge E from the T. So suppose this was my tree T, and my edge is this. Say, edge is this. This edge. This is my edge E. So it contains. So I have to produce an MST which doesn't contain this. So what he does, you remove this particular edge. You just remove this edge. Right? So after removing this edge, how many components this tree will have? Exactly 2 components. And the original graph was disconnected. So from this set to this set, now this set to this set, so there may be several such edges going. One of them was the edge that we have deleted. Okay, disconnected from this thing. Let F be an edge of C. Okay, disconnected, and we have different component of this. Let F be an edge of C. Where is C?
Cycle. The removed edge, so that
Okay.
is there in some cycle, right? So therefore there is an edge between them.
No, that okay. So that yeah, the heaviest cost edge in the cycle. Okay, that cost was in this edge that we have removed was in a cycle C. Which cycle? So it will go somewhere from here, something, and then come over here.
Yeah.
Right. And since if you delete it, this becomes disconnected. At least one of the cycle F will be going from this to this. So I call this my F. I remove this one and add this F. So F cost will be weight of F will be less than equal to weight of E, because E is the heaviest cost edge in the cycle, that particular common cycle, right? So I remove E and add F. Now T dash is a spanning tree of this, and weight of F is less than equal to weight of E. So T dash is also MST of G, not containing E. So I have constructed one more tree. That is a minimum spanning tree, but the edge E is not present in that particular tree. Is this clear?
Yes, sir.
Yes. Okay. Okay. So okay. So now it is time to have a break, and then we'll continue. Yes.
Yes, sir. Yeah, next time
4 to
you can
5:30.
talk.
So
Yeah.
6 o'clock we'll continue. I'll complete this part and then maybe I'll go to NP completeness. That is what I
Yeah.
promised yesterday.
Yeah,
Right?
yeah.
Okay. Okay.
Okay, sir. Okay.
Okay.
We will
From
do
this
that.
side, from this I continue something quickly. I'll tell. Prove we can see later on also. Idea I'll tell. So you'll get a feel that okay, this is how it is done.
Okay, sir. Yeah.
Okay. Okay.
Thank you so much.
Okay.
Thank you, sir.
Okay, participants, so we will meet again after 30 minutes break. You can take break.